Today I start replacement theorem. Okay, today we start replacement theorem. Obviously one important theorem in that means linear algebra, obviously especially in vector space related to basis dimension. Okay, and we also discuss this replacement theorem. Okay, replacement theorem. Okay, then we're also going to discussion about that. Okay, first we write this statement of this theorem here. Okay, statement. That means let P be a vector space. Let P be a vector space. Okay, let P be a vector space that is generated by a set. That is generated by a set. Generated by a set. Okay, G containing exactly n vectors. Okay, containing exactly n vectors, and let L be a linearly independent subset. L be a linearly independent subset of V. Okay, containing exactly m vectors. Containing exactly m vectors. Okay, then what happened? Then m less than equal to n, and there exists a subset, okay, h of g containing exactly n minus m vectors. Okay, such that L union H generates V. Okay, L union H generates V. Understood this one? Okay, this one we write it replacement theorem. Okay, we discuss it too easily. This one is important theorem in linear algebra. Obviously says about that P be a vector space, okay, that is generated by a set G containing exactly n vector, and L be a linearly independent subset of V containing exactly m vectors. Then what happened? M less than equal to n, and there exists a subset H of G containing exactly n minus m vectors such that L union H generates V. Okay, so we discuss this one. Now we're going to prove of that. We write here proof, and we write it in this way. The proof is by mathematical induction on A. The proof is by mathematical induction on M. Okay, the induction begins with m equal to 0. The induction begins with m equal to 0. Okay, then what happened? For in this case L equal to 5, for in this case L equal to 5. Understood? So taking age equal to z, so taking age equal to z, okay, gives the desired result. Understood? Then we also further discussion of that. Okay, we write it here. That means now suppose that we erase that portion and going to further discussion of that. Okay, now suppose that now suppose that okay, the theorem is true for some integer. The theorem is true for some integer m greater than equal to some integer m greater than equal to 0. Okay, now we prove that theorem is true for m plus 1. Okay, now we prove the theorem is true for what? M plus 1. Understood? Then let L equal to v1 v2 dot vm plus 1. Understood? Be a linearly independent subset of V. Be a linearly independent subset of V consisting of m plus 1 vector, consisting of m plus 1 vectors. Okay, then what happened? Then obviously v1 to vm is linearly independent. Okay, and we may apply the hypothesis here, v1 to v2 dot vm, okay, be linearly independent, be linearly independent. Okay, so we may apply the induction hypothesis, and so we may apply the induction hypothesis. Okay, we may apply the induction hypothesis to conclude that m less than equal to n. Okay, then what happened? That means L equal to v1 v2 vm plus 1 be linearly independent subset of V consisting m plus 1 vectors, and v1 v2 vm be linearly independent. So we may apply the induction hypothesis to conclude that m less than equal to n, and that there is a subset, okay, there is a subset u1 u2 dot here u n minus m, okay, of g such that of G such that P1 P2 Pm P1 P2 Pm union U1 U2 Un minus m, okay, generates P, okay. Then there exists scalar. Then what happened? Then there exist scalars, okay. A1 A2 Am A1 A2 Am and B1 B2 Bn minus m, okay, such that what? Such that A1 P1 A2 P2 AM PM plus B1 PM plus 1, okay, sorry, B1 U1 B not B U1 plus Bn minus m Un minus m equal to Vm plus 1. Understood? That means we talk about that this one, that means Pm and Un minus 1 generates P, so this one happen, okay. We marked it, that means star, okay. Then what happened? Note that n minus m greater than 0, okay, and let Pm plus 1 and let Pm plus 1 be a linear combination of okay, P1 P2 Pm P1 P2 Pm. Then what happened? Then obviously, that means then we see that L is linearly independent, okay. Then Pm is a linear combination of this one, okay, and then contradicts the assumption that L is a linearly independent. Then these contradict, okay, this contradict the assumption that, okay, this contradict the assumption that what? L is linearly independent, okay, contradict the assumption that L is linearly, okay, independent. Now we erase that portion and going to further discussion of that. Okay. Then what happened? Hence n greater than m, and that is okay, n greater than equal to m plus 1. Understood? Now we also see that for some bi p1 is not equal to 0, for some bi p1 not equal to 0. Then what happened? Then obviously we see about that, okay, we obtain some contradiction, okay. Moreover, some b1 not equal to 0, for otherwise we obtain some contradiction, okay. For otherwise we obtain some contradiction. We obtain some contradiction. Okay, we obtain some contradiction. Then what happened? Then obviously solving star. Okay, solving star for u1 gives what? Solving star for u1 gives u1 equal to minus b1 inverse a1, okay, v1, plus minus b1 inverse a2 v2, plus dot 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 minus b1 inverse am pm, okay, plus b1 inverse vm plus 1, okay. And here in this way, plus we write in this way, plus minus b1 inverse b2, okay, u2, and in this way here minus b1 inverse bn minus m, okay, un minus m. Understood? So then what happened? Then obviously that means we erase that portion and going to further discussion of that. Okay, okay, then we erase that portion and further discussion of that. Here we write let h equal to u2 u3 dot 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 un minus m, okay. Then u1 equal to, then u1 belongs to span of L union H, okay. And because okay, because v1 v2 vm v1 v2 dot 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 va, okay, hence u2 dot 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 un minus m are clearly in span of L union H, okay. It follows that what here v1 v2 dot 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 vm and u1 u2 dot 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 un minus m, okay, subset of span of L union H, okay. Because this one generates v, because this one generates v, okay, this one generates v, here u1 u2 dot 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 un minus m generates v, okay. Then what happened? This implies that what here span of L union H equal to v, okay. Since H is a subset of G, since H is a subset of, okay, since H is a subset of G, then since H is a subset of G, then what happened? That contains okay, n minus m minus 1 equal to n minus m plus 1 vectors. Understood? Then the theorem is true for m plus 1. Then the theorem is true for m plus 1. Understood? Then what happened? We also prove this replacement theorem. Okay. We first also going to the discussion on just mathematical induction on m. Okay. So in this way we also prove this one. Understood? I think not a problem at all. So we erase that portion. Okay. So we erase that portion now. Now we also going to discussion about some corollary related to that topics. Okay. Corollary 1. Okay. Let V be a vector space. Let V be a vector space. Okay. Having a finite basis. Having a finite basis. Then every basis for V contain the same number of vectors. Then every basis for V contain the same number of vectors. Then every basis for V contains the same number of vectors. Okay. Now we write here proof. Okay. What happens? Suppose beta is a finite basis for V. Suppose beta is a finite basis for V. Okay. That contains exactly n vector. That contains exactly n vectors. Then what happened? Okay, then we select a subset S of gamma containing exactly n vectors. Okay, that means we also take that let gamma be any other basis for V. Okay, if gamma contains more than n vectors, okay, then what happen? Then we can select a subset. Okay, then we can select a subset S of gamma containing exactly n plus 1 vectors. containing exactly n plus 1 vectors. Since S is linearly independent and beta generates V, since S is linearly independent and beta generates V, okay, then what happened? Then the replacement theorem implies that, okay, then replacement theorem implies that what? Implies that n plus 1 less than equal to n. Okay, we erase our portion and going to further discussion of that. Implies that what? N plus 1 less than equal to n. One contradiction. Okay, therefore gamma is finite. Therefore gamma is finite and the number of m vectors in gamma satisfies, and the number of the number m of vector, the number m of vectors in gamma, okay, satisfies what? Satisfies m less than equal to n, and reversing the role of beta and gamma, reversing the role of beta and gamma, okay, we obtain what? We obtain n less than equal to m, okay. So what happened? Well, so hence m equal to n. Understood? Then this one is not a problem at all. That means first we discuss the replacement theorem and obviously related corollary. Okay, we also discuss related corollary of replacement theorem. So what we then means do in here, if V be a vector space generated by a set Z and exactly n vectors, then L be a linearly independent subset of V contains exactly m vectors, then m less than equal to n, and obviously there exists a subset H of G containing exactly n minus m vectors such that L union H generates V. Okay, and in this way we also prove this replacement theorem, and obviously this corollary state about that V be a vector space, then every basis for V contains the same number of vectors. Okay, so today we discuss two easy portions, and I think all are understand this because this one is a consequent step-by-step problem, and obviously one easy steps are here, so all are understand this. So if you get this type of video, please subscribe my channel, and if you gives like, please click on like options. If you have any questions, comments, suggestions, write it in comment box. Okay, so today I'll stop here. Thank you.